Today we're going to talk a little bit about energetics and temperature scales, things like that, and how we actually measure heat. Two important definitions are exothermic and endothermic. Exothermic is a process that releases heat, whereas endothermic is a process that absorbs heat. So some phase changes require that you put heat into them, and others require that you take heat out of the substance. So if you think about something freezing, heat has been leaving it. So some of the definitions that we talked about last time, or some of the phase changes that we talked about last time, we can categorize as being either exothermic or endothermic. So if we're going to be putting heat in, remember, putting heat in is endothermic, taking heat out is exothermic. So if we think about something like sublimation, where we're going from a solid way up to a gas, a lot of heat is going into that sample. So that sample is taking heat in, so that is endothermic. If you think about something melting, so in order for something to melt, we have to put heat into it. If you think about fusion, that's the same thing as melting. It's just another version of another word for that. Condensation, heat is actually removed, so heat comes out of the sample, so that's exothermic. Evaporation, we're putting heat in from the surroundings. Deposition, so we go from a gas down to a solid. So we have to have energy leaving the sample. And over here we've got vaporization. That's another version of becoming a gas. And last but not least, we've got freezing. So we're actually removing energy from a sample in order to freeze it. So we can check, see how we did. Good. I hope I did all right on those. The way that I like to think about this too is if you think about your sketch of a heating or cooling curve. And, in terms of solid, liquid, gas, and where these transitions are. So condensation is a gas to a liquid. That's actually going down on that curve. Deposition, gas down to solid. You're going down on that curve. Freezing, you're going from a liquid down to a solid. If we look at the ones over on the endothermic side, sublimation, that solid to a gas, goes up on the curve. Melting, solid to liquid, you go up on the curve. Vaporization, liquid to gas, you go up on the curve. Solid to liquid for fusion, you're going up. Evaporation is liquid to gas, you're going up. So if you're on a heating curve, you're putting heat in, those are all endothermic changes. If you're on a cooling curve, you're removing heat, those are all exothermic changes. It is important to remember there's no such thing as cold, only the absence of heat. So when you actually say that something is that it's cold outside, for example, all you're saying is that it's not very hot. So we can measure heat, but we can't actually measure cold. What heat actually is it's a form of kinetic energy. Specifically, we call it thermal energy. It has to do with vibration in molecules. Heat is measured by measuring temperature. Heat always flows from where there is more heat to where there is less heat. So hotter to colder, if you will. And cold is really just the absence of heat. So cold is really just not hot. So one thing you need to be able to do is draw a heat flow diagram. So if you imagine you had a typical room temperature room with a table and you put an ice cube on it, remember that heat is going to flow into the ice cube. From the table, heat is going to flow into the ice cube from the air. If you touched it with your hand, the reason it feels cold to you is heat is leaving your hand and flowing into the ice cube. So you always want to make sure you're going to go from the thing that is warmer or of a higher temperature to colder or of a lower temperature in a heat flow diagram. So in terms of what's going on with phase changes, I kind of like this diagram because the direction of the arrow kind of relates to what's happening with energy being put in or taken out. Kind of looks like a heating or cooling curve. This kind of does the same thing. We'll be talking about heat of vaporization, heat of fusion a little bit in the next set of stuff that we're doing. But I kind of think if you're going up, remember you've got to be putting heat in. If you're coming down, you're removing heat. There are two main temperature scales that we use. We do not use Fahrenheit. We only use Kelvin and Celsius. Temperature actually means, or temperature is, a reading of the average kinetic energy in a sample. What's very important to understand about temperature is a measurement of energy, not a form of energy. We will not use the Fahrenheit scale because it is not an international scale. It's only a American scale, so it doesn't really have a lot of use in a lot of other places. And actually, the Celsius scale is extremely useful and based on water, which makes it very helpful to us. If you go to table T on your reference table, you're going to find, if you go all the way down to the bottom, you can find the relationship between Kelvin and Celsius temperature. So you have a little equation for this that allows you to convert between the two units. So very important to keep in mind that heat is a form of kinetic energy. Temperature, is a measurement of kinetic energy. So I like this diagram because what's nice about the Kelvin and Celsius scale is even though the numbers on them are different, the graduations are the same. What I mean is a change in 1 degree Celsius is the same as a change of 1 degree Kelvin. So if I look at my freezing point of water, my freezing point of water in Celsius, you probably already know, is 0 degrees Celsius. Boiling point is 100 degrees Celsius. If I look at those same numbers on my Kelvin scale, I have 273 Kelvin and 373 Kelvin. The difference between them is 100. So the Celsius scale is actually a relative scale that's very convenient for what water is based on. The Kelvin scale goes all the way down to 0 Kelvin where you have absolutely no energy. So Kelvin is considered an absolute scale because 0 Kelvin is 0 energy. You have 0 molecular motion whatsoever. We've actually gotten very, very close to absolute 0. It's a very expensive thing to do, but we are within decimal points of a degree. So we don't use Kelvin a lot because it's kind of weird to think about water being, or an ice cube being 273 Kelvin. We relate a lot more easily to water. The Celsius scale used to be called the centigrade scale, because centa means 100. So they basically took the difference between the freezing and boiling point of water and divided that by 100, and it made a very useful scale for us. Most of the time we will use Celsius, depending on the types of calculations we're doing. Sometimes we'll be using Kelvin as well.